Welcome back to the deep dive. You know, we're covering something today that, well, it really feels like a huge blind spot in this whole AI boom. We spend so much time talking about how big these models are getting, GPT-4, Gemini, these massive context windows. We know they can see and hear and read all at
Right,
once.
multimodal AI. It's really the standard now.
It is. But here's the thing that really struck me reading today's paper. We just assume that because an AI has eyes and ears, it's, actually combining those senses in a smart way. But it turns out we haven't really known how that combination actually happens.
hmm
We've basically been treating the interaction part of it all as a total black box.
It's a classic case of, well, it works, so don't ask too many questions.
hmm
We feed a model video and audio, it gives us a prediction, and we just kind of assume it understood the relationship.
But knowing that it works is so different from understanding why it works.
Exactly.
And that is the exact gap this paper is trying to fill. We are looking at quantifying and modeling multimodal interactions, an information decomposition framework. It's from a really heavy-hitting team. Paul Pouliang and his colleagues from CMU, Princeton, Harvard Medical School.
A serious group.
And their goal isn't just to build another model, it's to build a ruler.
A mathematical ruler, to be precise.
Yeah.
They are trying to measure the flow of information. So when you have two different inputs, say the tone of someone's voice and the words they're actually speaking, how much information is coming from each one on its own, and more importantly, how much comes from the collision of the two.
That idea, the collision, that's so central here. The paper uses a framework called PID, Partial Information Decomposition. Before we get into the heavy math of how they actually calculate it, we should probably just understand the vocabulary. They break information down into three buckets: redundancy, uniqueness, and synergy.
Right. These are the three pillars of the whole framework. And I mean, while they sound like simple English words in information theory, they have very, very strict definitions.
Okay, so let's start with redundancy. In a normal conversation, calling something redundant is usually, an insult. It means it's useless.
Yeah,
But here, the paper argues redundancy is actually a feature, not a bug.
that's right. In this context, redundancy, or R, refers to information that's shared between the modalities. The classic example is seeing a dog bark and hearing a dog bark.
Okay.
The visual of the jaws snapping, that tells you dog barking, and the audio of the woof also tells you dog barking.
So if I lose the audio, I still know what's happening.
Exactly. Redundancy provides robustness. It's a good thing. If you're building a self-driving car and it's foggy out, you want the radar to tell you the same thing the camera would have. You want that safety net.
Okay, that makes perfect sense. Then we have uniqueness, or U. This one feels pretty straightforward. It's just information found in one place.
Right. Think of a silent movie. The visual channel has unique information that just doesn't exist anywhere else. If you're an AI model and you ignore that unique visual data, you're going to fail.
Okay, so far so good. This feels intuitive. But the third bucket, that's the one that really makes you stop and think. Synergy, or S. It's the ultimate corporate buzzword, but in this paper it means something incredibly specific.
Synergy is the measure of emergent information. This is information that is not in source A and it is not in source B. It only, and I mean only, exists when you know both A and B at the same time.
I want to pause on that because it almost sounds like magic. How can information just appear out of thin air because I combined two things that didn't have it?
Well, it's not magic, it's context. The best example, and they come back to this later, is sarcasm. Imagine I send you a text that just says, "Great job."
Okay, on its own, that's positive sentiment.
Now, imagine I leave you a voicemail and my tone is just flat and monotone. "Great job."
On its own, a flat tone is just, I don't know, neutral, maybe tired, not necessarily negative.
But when you combine them, the positive words plus that flat tone, you get sarcasm. The sarcasm wasn't in the text. It wasn't in the audio. It emerged from the interaction. That's synergy.
Wow. So an AI looks at the text, says happy, it looks at the audio, says neutral. It's only by measuring the synergy that it can get the right answer, sarcastic.
Precisely. And this is where the history here gets really interesting. You asked why we haven't been measuring this all along. I mean, we've had information theory for decades. There's a metric called mutual information. Why not just use that?
The paper seemed pretty critical of it, basically said the old ruler was broken.
It was. There's a specific formula called interaction information, and for a long time that's what people used. But it has this mathematical flaw in how it handles our three buckets. In that old formula, redundancy adds a positive value, but synergy contributes a negative value.
Wait, so they cancel each other out?
They can, yeah. Imagine you have a complex data set that's highly redundant, so lots of safety checks. but also highly synergistic, lots of complex interactions. If those values are roughly equal, the old mutual information formula just sums them up and it gives you 0.
So the math tells you nothing to see here, when actually there's a ton of complex activity going on under the surface.
It's a false negative. It completely masks the complexity. And that is why PID is so necessary. It forces us to decompose that 0 result into positive redundancy and positive synergy instead of letting them hide each other.
That explains why this has been such a black box. We were literally using a tool that couldn't tell the difference between a simple system and a complex one. But okay, knowing we need PID is one thing. Calculating it seems like a total nightmare. The paper says you need to know the probability of every possible state of the data.
And for high-dimensional data, that's just impossible. Think about a single video frame. Millions of pixels. Each pixel can be one of millions of colors. The number of combinations is, it's effectively infinite. You just can't do it.
So this team, Liang and his colleagues, they had to invent a workaround. They proposed 2 different estimators ways to approximate these values. The first one is called CVX.
CVX, right? That stands for their convex optimization approach. This is essentially the exact solver, but for simpler problems. Optimization is a math technique where you try to find the best possible solution given a set of constraints.
So CVX is trying to find a probability distribution that fits the data we have, but with the fewest possible assumptions.
Yes. It searches for a distribution that matches the known statistics of the data while minimizing the interaction information. It's incredibly accurate, but it's very heavy, computationally speaking. It works great if your data is, say, yes, no. But if you feed it a raw video stream, it just chokes.
Which brings us to the heavy lifter, BTCH. This feels like the real innovation for modern AI.
BTCH is what makes this whole framework usable for things like deep learning. Instead of trying to solve the optimization problem perfectly, they train a neural network to estimate the distribution.
But how does a neural network even handle the strict rules of probability? The paper mentions something called the Sinkhorn algorithm.
This is a fascinating piece of math. A probability distribution has to follow rules like all the possibilities have to add up to 100% or 1.0. A standard neural network just spits out numbers, doesn't really care if they add up. The Sinkhorn algorithm is a clever way of forcing a matrix of numbers to become doubly stochastic.
Doubly stochastic. Okay, break that down.
It just means that if you have a matrix of probabilities, every single row sums to 1, and every single column also sums to 1. The algorithm just iteratively scales the rows and columns over and over until they snap into that perfect grid. It forces the wild output of a neural net to behave like a proper, strict probability distribution.
And that's what allows them to apply this PID framework to messy, continuous data like audio waves and pixel gradients.
It bridges the gap. We go from this abstract theory, synergy exists, to a concrete tool where I can feed in a gigabyte of video and get a number back that says, this has 40% synergy.
So they built the ruler, then they went out and started measuring the world, and they found that not all data sets are created equal. They make this distinction between 2 types of interactions, mediation and moderation.
This is really the so what of the whole measurement process. Once you run BATCH on a data set, you look at the relationship between redundancy, R, and synergy, X.
So if R is greater than S, they call it mediation.
Right. Mediation implies that one modality is essentially passing information through another. The information is shared. It's just like our dog barking example. The audio mediates the exact same concept as the video.
And if synergy is greater than redundancy, S is greater than R, we get moderation.
Moderation is the really interesting one. This means one modality is actually changing the meaning of the other one. It moderates the signal. Sarcasm is a moderation effect. The tone moderates the text from positive to negative.
So did they find that real-world tasks actually split cleanly along these lines? Or is everything just a big mix?
They found very clear distinctions, and it really validates the intuition that, we've had for years but couldn't actually prove. For example, they looked at instructional videos, like a cooking tutorial.
I would guess those are super redundant. You see the chef chop an onion, you hear the chef say, chop the onion.
Exactly, and the data showed that, high redundancy. But then they looked at something like sentiment analysis or pathology diagnosing disease from medical scans. Those were highly synergistic.
Let's dig into that pathology case study, because that feels incredibly high stakes. If I'm a doctor using an AI to detect cancer, I need to know how it's making its decisions.
Right, this was a collaboration with Harvard Medical School. In pathology, we're looking at these huge, high-resolution slides of tissue. You have the visual texture of the cells, and you have their special arrangement where they are.
And the paper suggests the cancer signal isn't just in the texture, and it's not just in the location either.
It's in the interaction. The study found that pathology tasks are synergy dominant. This means the disease signature emerges from a specific combination of cell shape and cell neighborhood.
Now, here's the scary part for me. If I train a standard AI Model 1 that doesn't know about PID, and that model just happens to be really good at finding redundancy, it's going to completely fail at this task, isn't it?
It will fail, or even worse, it will give you a low-confidence answer that looks okay, but misses that critical insight. And this is the model selection application. The researchers show that different AI architectures have different inductive biases. Some are basically redundancy hunters, others are synergy hunters.
So before we even train a model, we should run this PID analysis on the data. And if the data comes back and says high synergy, we pick the synergy hunter architecture.
You got it. It's diagnostic. You don't just throw a ResNet or a transformer at every single problem. You diagnose the data's complexity first.
They also applied this to robotics. I found the autonomous vehicle example really compelling because it highlights the danger of just assuming redundancy.
Right. In robotics, you usually have a camera and a depth sensor, like LiDAR. Most of the time, driving is redundant. The camera sees a clear road, the LiDAR sees a clear road.
But what happens when they disagree?
That is the critical moment. Let's say the camera sees a green light, but the LiDAR detects a large object right in front of the car. Maybe it's a glitch, maybe it's a truck with a weird reflection.
If the model's just looking for redundancy, it might try to average those out. Well, one says go, one says stop. Let's just go slow.
Which causes a crash. The disagreement is the information. The fact that the sensors conflict is a synergistic piece of data that essentially streams danger, unknown state. A synergy-aware model treats that conflict as a new, unique signal that should trigger a safety protocol. A redundancy-focused model might just treat it as noise to be filtered out.
That distinction, seeing conflict as information rather than noise, that seems like a fundamental shift in how we should be thinking about sensor data.
It really is. It moves us away from just, smoothing over errors.
The third application they mentioned brings us back to the social side. Mood prediction. We talked about sarcasm. But they looked at this data set called Mosei, which is just thousands of clips of people expressing sentiment.
And no surprise, they found that human emotion is incredibly synergistic. This has huge implications for things like customer service bots or, say, mental health AIs.
Of course, because right now, so many of those bots just look for keywords. If I type, I love waiting on hold for an hour, the bot just sees the word love and thinks I'm happy.
Right. That is a total failure of redundancy processing. It's taking the text at face value. A model that was optimized for synergy would look for the mismatch between the context waiting on hold and the sentiment love, and it would identify the frustration.
Okay, so if we zoom out, this paper gives us a framework PID, gives us the tools CVX and BSCH. And it proves the world is sort of split between redundancy and synergy. What's the takeaway for the person listening who isn't, coding a neural net tonight?
I think the takeaway is about the definition of understanding.
Yeah.
We often think of AI as just pattern matching, but this paper really suggests that true understanding, whether it's diagnosing a tumor or just getting a joke, requires this very specific mathematical quantity of synergy.
It effectively creates a metric for insight.
It does. Insight is arguably the ability to connect two things to create a third new thing.
That is a really provocative thought. If synergy as the whole is strictly greater than the sum of its parts, are we getting closer to actually quantifying something like creativity?
I think we are. I mean, if you look at a great piece of art or a brilliant scientific theory, it's usually a combination of existing elements that create something totally new. If we can measure that in pixels and audio waves, maybe we can eventually measure it in ideas.
It really raises the question, are we building AIs that can just copy, which is redundancy, or AIs that can actually create synergy?
And up until now, we couldn't really tell the difference. But now, we have the ruler.
So next time you see a headline about some new multimodal AI, ask yourself, is it just seeing and hearing the same thing twice? Or is it actually finding the synergy?
It's the difference between a parrot and a poet.
That is a perfect place to wrap it up. Thanks so much for walking us through the math today.
My pleasure. It was great.
And thank you for listening. Keep looking for the synergy in your own world. We'll see you in the next deep dive.